Hi everybody, welcome back. This is example 8.4a. Actually, we're going to do A and B together here. And I kind of need to back up a little bit here. I had meant to do this example separately, but I do want to kind of tie it into a slide from our notes. So the previous slide in our notes went as follows. The net work that is done, all right, all the sum of all the work that is done is equal to, well, the sum of all the works that are done, be they positive, be they negative. All right, so you just add them all up, and you get that's a sigma right there. It's the sum of all the works, which is another way of saying our net work. All right, so that's going to be the principle on which we do example 8.4a. All right, let's take a look at this. All right, so we have a car. Once again, we don't have any knowns right here, but that's okay. We're just going to write it out, and so if you knew your knowns and if you knew your distances, you'd be able to solve for it. But we're going to compare this to part B and see how one is definitely easier than the other. All right, so I'm going to draw my car. Let's see, I'll draw it up on the corner right here. All right, so there's our angle. Here's our car right here, and it's coasting down a hill. All right, so what we want to do is we want to label all the forces that are on it. All right, well, we have the force of gravity, all right, straight down right there, mg, and of course that creates two forces that we know to be force perpendicular and the force parallel. Force parallel right there. There's also a normal force that is mentioned. Now it's labeled F sub n. We just call it n. All right, and there's also a force that is acting against the movement of the car up the hill, or just against the direction of the car's movement, which we'll call, looks like I'm writing fair, but it's the force of air resistance, all right, resisting the movement of the car. I usually do resistance or friction forces as a lowercase. Here it's mentioned as an uppercase. It doesn't really matter. Okay, so these various forces are working on the car. Well, let's sum up I'm sorry, let me finish reading it right here. It travels down the road, all right, the car travels down the road, distance d. All right, so I'm going to mark that in, I don't know, light blue right here, okay? So that is our d distance, whatever that may be, all right? So if we want to find the net work, or the sum of all the work that is done right here, what do we have to do? Well, we have to add them up using our description of work. All right, so we know that in any case, work equals force times distance times the cosine of the angle between them. So we can say the net work equals what? Now this is going to be kind of long right here, and hopefully I don't run out of space, but I think I'll be all right. In fact, I'm going to move this down a little bit, and right down towards the bottom. Net work is the sum of all these works right here, so let's just do them piecemeal. Okay, what are all the forces doing work on this car? Well, let's do the first one, and I'll write that in green. That's going to be the force parallel times distance d times the cosine of the angle between them, right? And, well, in fact, I'm going to just back up here. What is the angle between them? We'll do this a little bit more simply, all right? What is the angle between the force parallel and the distance d? It's 0, right? Because they're basically in the same direction. So cosine of 0 degrees. All right, so we have that description of the force parallel going down the hill, doing some work. All right, so I'm going to put that in brackets right there. So we're going to have some other work that's being done. What is that? Well, I'll write this one in blue because I'm going to do the force created by or the work done by the force perpendicular, right? Force perpendicular times d times the cosine of what's the angle between the force perpendicular and the distance d? Well, that's 90 degrees. 90 degrees right there. And that describes the work done by force perpendicular. All right? By the way, what is the cosine of 90? It's 0. Right? So this force right here, which is at right angles to the direction of motion, is doing no work. But that's okay. We'll just continue to write it out. All right, the third force that is working right here. What do you want to do next? You want to do normal force? Let's do normal force. All right, normal force times distance d times the cosine of the angle between them, which is, oops, I meant to write a phi right there. I'm just going to write in the actual angle. What is the angle between the normal force and the distance? It's 90 degrees. And that, too, is going to go away because cosine of 90 is 0. Finally, we have our last force, the air resistance force. Let's see what kind of work that's doing. So that's the air resistance force, whatever that may be, times the distance d, times, what's the angle between this force and this direction of motion right here? That's 180 degrees, right? It's a 180 degree difference. So what's a cosine of 180? Cosine of 180 is -1. All right, so the air friction is doing negative work. The force parallel is doing positive work right here, and depending on what they are, it'll roll down the hill or maybe it won't. All right, so if you wanted to find your sum of all your forces, you could do it this way. Force times distance times angle. Force, distance, angle. Force, distance, angle. And we can't go any further right here because we don't know any knowns. But we're going to see in example 8.4b how we can actually make this process a little bit simpler. All right, so we're going to look at another way to sum up the net work on an object, and then go ahead and apply it, and I think you'll find that will be simpler. So thanks for watching. I'll see you in example 8.4b.